How to power our projects is an important question. In this video, I will focus on mains-powered projects and try to establish a step-by-step approach to get to the right decision. Grüezi YouTubers, here is the guy with the Swiss accent, with a new episode and fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you will always sit in the first row. In this video, we will start with the needs of our project. Look at the different available possibilities to connect the project to mains. In a future video, we will probably do the same for batteries. And finally, find the right questions to ask to find the right solution. I also will provide a decision tree. Let's start with the properties of mains power as an energy source for our projects. Mains power is quite simple if we focus on small hobby projects. Its capacity is unlimited compared with our needs. Its voltage is quite constant. It is very cheap if used in small doses, and it has no relevant current limits. First, we always need a power supply that transforms 110 or 220 volt AC to a low DC voltage. For simplicity, I distinguish between USB power supplies and others. All USB power supplies can deliver 5 volts and at least 1 ampere. Most of the newer power bricks deliver 2 or more amperes. So they definitely are an excellent choice also for Raspberry Pi projects. I still have lots of these old bricks with different voltages like 9 or 12 volts. And I still use them because they are easy to use, and, the more important reason, it is far easier to mount a round power jack than a micro USB plug into my cases. If your project needs more oomph, you get those bigger power supplies. They all look similar and you get them for all voltages and amperages. It is good to have a few laying around in your lab, just in case. One of those is inside this power supply, for example. And you get these PCB power supplies for smaller projects. They can be used if you do not want to have a separate case for your power supply. But you have to pay attention if you use one of those, because the mains voltage gets very close to your project. So definitely the preferred solution is a USB power supply. And if you watch video number 244, you even can pimp them up to at least 12 volts if they are QC compatible. As the next point, we have to divide the needs of our projects into categories: 5 volt projects, 3.3 volt projects, and other or mixed voltages projects. 5 volt projects mainly use old Arduino boards or are powered through USB. 3.3 volt is the new standard. Also, the newer Arduino boards use it. And others are projects which need higher voltages because they use motors, for example. How can we connect the power sources with our projects? Here we can mainly distinguish between 4 possibilities: a direct connection, linear regulators, switching regulators, and others. If the output voltage of our power brick is the same as the voltage of our project, we can directly connect it. If our project needs different voltages, or if the power supply voltage is higher than the project voltage, we need voltage regulators to drop it. In mains-powered projects, you rarely find so-called boost converters, which create a higher output voltage. Usually, you start with the highest needed voltage. We will cover boost converters in the batteries video. Linear regulators destroy the voltage difference between the input and the output by converting it into heat. Therefore, they have a terrible efficiency, which is not critical for mains-powered and low-power projects. Switching regulators transform the voltage by switching the power supply on and off. This usually creates some noise on the output wires as well as in the air around the device. But they are very efficient. And others include unregulated power supplies as well as power supplies which only use capacitors and resistors for very low power. We will not cover this category in the video. Let's now take a typical project to find out the questions we have to ask. This recently built Morse trainer consists of an ESP32, a small audio amplifier, and a PS2 keyboard. The first question is, mains or battery powered? I will use it in my lab and therefore it can be powered by mains. So it fits in today's video. The next two questions we have to ask are, which is the highest voltage our project needs? And how much current does it consume? The ESP32 can be powered by 3.3 volts, the keyboard runs on 5 volts, and the audio amplifier needs at least 5 volts. Better would be more because it would provide a louder tone. The current will be quite small, for sure less than 200 mA with short spikes produced by the ESP32. But with a big capacitor we can reduce these spikes. So what is the highest voltage used by this project? We could say it is 5 volts because also the audio amplifier would work at that voltage. I decided for a 9 volts supply because I still have a few of them lying around and I can power the amplifier with a higher voltage. In addition, with this 9 volts input, we can learn on how to dimension a linear regulator. I decided to use one of those Wemos ESP32 boards because I still have a few of them from my various tests and because I anyway need 5 volts for the keyboard. So our drawing looks like that. 9 volts in, directly connected to the audio amplifier. By the way, as long as you connect all grounds, you can have as many voltages as you want in parallel. Next, we need a 5 volts power supply for the keyboard and the Wemos. Here the following question has to be answered. Shall we use a linear or a switching regulator? This depends on the following two questions. How much power has to be dissipated by a linear regulator, and can we live with noise on the power cables or in the air? Cable noise can be heard in audio applications and air noise can disturb sensors or radios. For example, many viewers report false alarms of PIR or radar sensors because of proximity of an ESP Wi-Fi antenna, which emits some energy or noise into the air. Our application can comfortably live with a little noise. We do not want to listen to classical music just to a Morse signal. So we have both choices, a linear and a switching regulator. But what about the power dissipation? Because linear regulators usually are small parts, I would like to use such a 7805 regulator in a TO220 case. The smaller 78L05 with its 150 mA limit would be too small. The dissipated power is 9 minus 5 volts times 0.2 ampere equals 0.8 watts. Because the heat is created inside on the junction of the chip and has to be transported to the air around the case, we have to find the value for the thermal resistance from junction to ambient. It is called theta and measured in degrees centigrade per watt, and also depends on how the part is cooled. If we do not cool the TO220 case, this factor is around 60 degrees Celsius per watt. So the silicon chip will heat up 60 times 0.8 watts equals 48 degrees. We could reduce the degrees per watt if we mounted the regulator to a heatsink or solder it to a PCB with lots of copper. If you are too lazy for that calculation, you choose the Swiss guy method. Power it up with the maximum expected load and put a finger on the regulator. Just make sure you really put the finger on the regulator, otherwise you might see some magic smoke. Because smaller cases have values of more than 100 degrees per watt, they heat up faster. This is probably one of the reasons the 78L05 in a small TO92 package only is rated for 150 mA. By the way, all those linear regulators need these two additional capacitors to run stable. And you get those regulators for different voltages and even an adjustable voltage version. All have in common that they have a minimal dropout voltage. This means that the input voltage has to be higher than the output plus dropout voltage. We will later see that a low dropout voltage is essential for battery-powered projects. For projects connected to mains, it is usually not critical. The other important parameter, quiescent current, is also not relevant for mains-powered projects. Of course, we could have used a small switching regulator like this one. It is not much bigger than the TO220 case of the 7805, has a maximum input voltage of 12 volts and a maximum current of 2 ampere. It has a tiny trimmer to set the voltage. Not convenient and even dangerous, because if unintentionally moved towards a higher voltage, the overvoltage quickly kills your MCU. Maybe it is good practice to put some hot glue on the trimmer to fix the voltage. A much better solution is this board with fixed voltages. You just place a solder blob where needed and you are sure the voltage stays correct. Here is the promised decision tree, and we can see what we did. The highest voltage is 9 volts, a linear 7805 can easily dissipate the power, and we could live with noise. In principle, we could use a linear or a switching power supply. Because the 7805 is small, I decided to go with this one. Let's go on with the next possibility, an Arduino project without other components. Here we can use a USB power supply or one of those fixed voltage ones for 7 to 12 volts. The 5V Arduinos all have linear 5V regulators and a second one for 3.3 volts. The second one is connected to the 5V rail and therefore can be smaller, so they used a similar decision tree for their decision. By the way, I used the word rail. This word is commonly used if you have more than one voltage in a device. Each voltage has its own distribution rail. Next case, the highest voltage of the ESP development boards is 5 volts because of the USB to serial chip, and they also need 3.3 volts for the ESPs. So 5 volt is the highest voltage, and they go this route and use a AMS1117 linear regulator for their 3.3 volt rail. These boards usually have no 5 volt regulators, and therefore you would blow up the USB to serial chip if you used more than 5 volts. And if you are out of luck, also your PC. By the way, switching regulators also can get hot. The calculations for these regulators are much more complicated and generally not the chip itself, but the inductor gets hot. So put your finger on this part too if you use the sophisticated Swiss Guy method. A word to power supplies in general. For most applications, USB power supplies are more flexible than these old-fashioned bricks. They can be used for many purposes. Especially QC-rated supplies are fascinating because we can make them deliver 9, 12 or even more volts, as shown in video number 244. Why not power delivery or PD supplies? Because this technology is still hard to handle for makers. I do not know how to make them deliver 12 volts, for example. And all those USB power supplies are of the switching type. Otherwise, it would not be possible to create such small and powerful devices. Old-fashioned power supplies use 50 Hz transformers to reduce the voltage, use a full bridge rectifier and beefy capacitors to create DC, and then a linear regulator. These power supplies still are the first choice if you do not want to have noise. Typical for high-end audio applications, for example. But they are big, heavy and expensive. And how can you distinguish between conventional and switching mode power supplies without opening the case? No, you do not need expensive instruments. Just lift them. Then you know. Summarized, always start with the highest needed voltage. Use the decision tree to get to the right decision on how to power your projects. It shows when to use linear and when switching power supplies. And always use at least the Swiss Guy method to dimension the regulator or the heatsink. This is all for today. Please comment if I should do a similar video about battery-powered devices. As always, you find all relevant links in the description. I hope this video was useful or at least interesting for you. If true, please consider supporting the channel to secure its future existence. Thank you. Bye.